So I'm going to talk about results and developments we have with two projects that relate to searching for ET and extraterrestrial probes. Let us start first with a mind experiment. Imagine if, instead of searching or instead of waiting for a UFO to hover over your head, you could actually use some kind of technique to search for unidentified objects that are non-human, and not only to do these searches, but also, in case you detect it, directly get a spectrum in real time that would characterize it, directly localize it in 3D so that you know where it is, and directly validate it with multiple instruments so that you know that nothing here is wrong. And imagine now that you could also do that and get rid of all human objects, let's say satellites, space debris, and you know that that's not human. I would be quite interested in such an experiment. And I'm going to talk about a potential way how I can do that, more or less, in the second half of my talk, when we are planning to build a global network that permits us to, with help of wide-field telescopes and high-speed cameras, catch short flashes of light associated with non-human objects, either like fast reflections or short laser pulses or other kind of emissions. And the point of all this is that you want to really minimize the number of false positives, because scientists are sometimes a little lazy and you don't want to go through too much data. And you can find a paper in the brief where we describe the beginning of this project in February, where the goal is to detect, localize, verify, and reproduce any finding in real time. Because once you see such a short flash, you don't know when you're going to see it again, and especially if you see multiple of them, now you might have to wait years until you find it. And when our goal is not to find the thing that can't be identified. Our goal is to search for a specific, identifiable signature from an ET probe or non-human object, or UFO, or whatever you want to call it. And which means that we are narrowing it down quite a lot to a specific hypothesis. Our search range is going to be up to 150 million kilometers from the Earth. And again, this instant validation and instant spectra and instant localization is going to be the most important bit. And in this way, we will get spatial resolution, a time resolution, and a spectral resolution of any discovery. However, before I'm going to tell you about the project, I'm going to tell you about the history of why we want to do it this way, and not in any other way. Let's first think about the possibilities of life in the Milky Way. So many people are going to say, oh, but we don't know if there is any other planet except for the Earth that has life. But come on, let's think about the numbers. Just in the Milky Way, you have something like 200 to 300 billions of stars. You know that 22% of every sun-like star has an Earth within the habitable zone. Now, that is quite a lot. And if you count on that, you have about 40 billion of Earth-like planets just in the Milky Way, where there might be plenty of life. They have also found amino acids on asteroids and meteorites, and it will be so exciting to see what the OSIRIS-REx samples are going to actually tell us when they become analyzed. That's a fantastic project where they brought down a sample from an asteroid in September. So many of us are aware of how the first searches for extraterrestrial have been done, the first generation searches of SETI, which has been the radio SETI. Many people associate SETI with an institute, but SETI is actually a field of research, and where people have mostly been dedicated to these searches for their artificial radio signals. One has been using the Green Bank telescopes, and one is also using the Allen telescope array, and one is doing that since the 1960s, because this was the easiest way to look for ET. And I don't know how many of you are familiar with the movie Contact, where you have Dr. Ellie Arroway searching for radio signals, and she searches, and finally she finds them. And that's kind of what the movie is about. I'm sad to say that in real life, she's still searching. So one has also done very beautiful searches for lasers. And this is done in a much smaller extent because it is relatively new, because at the time as technology develops, you can do more and more things. And this has been done in the last years, and thousands of stars have been surveyed, not 300,000, but thousands. And so far, there is an optical desert. No lasers have been found so far. That should start getting us a little nervous, right? I engaged personally also in searches. So I was I'm leading a project called the Vanishing and Appearing Sources during a Century of Observation project, where I wanted to find a star that vanishes. Imagine a star that is there in multiple images, and you see it, and you really know it's there, and then one day it vanishes. That would be a beautiful technosignature of some completely new physics. And since 2016, I worked with my team of about 40 people, with machine learning scientists and astronomers, and we searched for these stars by comparing images from the 1950s to images to today. We didn't find a star that really was there and vanished, but we found a lot of weird transients. I will come back to that. Now, there is something very beautiful about these plates that we were using. We were using photographic plates that were done in 1950, and in the early 1950s. For those of you who know how these photographic plates works, they're usually quite big. They serve a big part of the sky, and there were very fine studies done at Mount Palomar, for example, in Lick Observatory, the Vatican. And one great advantage of these plates is that there were no satellites. We humans had not yet contaminated the sky. And airplanes are so easy to distinguish because you just get a streak. So they are excellent for searching for ET, but you go back in time. It's like a time machine to when your sky was before Elon Musk and similars. So we were actually searching for these vanishing stars by comparing these images from the 50s and with the images from like more or less today. And we analyzed terabytes of image data automatically and through a citizen science project that unfortunately I cannot show the animation of because I have some technical issues here. But it was really a big work where we looked through many objects, like one by one. And we found many short flashes that appear on one image and they don't appear again. They were appearing very shortly, briefly on these photographic plates and then just vanish. Something that vanishes at timescales less than 50 minutes. So that was quite interesting, but not as interesting as when we found 9 of them in a small region of the space that appear and vanish within 50 minutes. Because then we say as astronomers, oh, what on earth is that? The paper caused a lot of astronomers getting stressed over social media, saying that they should not be citing the paper because of some sociological issues. Actually, the same people who usually are going for AVI also went for me. Astronomers are bored sometimes. And what happened here is that we see these images. You see the green circles. You have ignored the purple circles that are scanning defects that we could distinguish by comparing different scans. But what you see is that on the 12th of April, you have 9 stars that are there in one image, or transients, as I'm going to say, for these short flashes. They are there in one image, and they are not there later. And they were not there half an hour earlier, they were not there 6 days later, and they never appeared again. And we used the big Gran Telescopio Canarias, and we searched for them with a deep imaging, and we found nothing. So we started thinking about all possible causes, astrophysical causes, and we couldn't explain it in any astrophysical way. They're so spread over the sky, and at the same time they have these very typical brightness profiles that come with real stars. So no, we couldn't explain that in any way. Now, instrumental issues. We could exclude a lot of the most common instrumental issues, and then some turned out to be very unlikely, and of course some of people think that maybe you have some kind of plate defects. It's just that these plate defects in such case would have to be first by chance, each one of them would have to be looking exactly like the stars and imitate the brightness profiles of the real stars. And also on top of that, you would need to have 9 of them, all coincidentally star-like and not a mix of various shapes. So it didn't look far too likely. Of course, this started in 2020 because we found an example in March 2020, right when the pandemic started. And in 2021, when we had our referee, he or she asked, how do you know that it's not just somebody who sneezed on the plates? And we had to look at the images, look at the size, and we could show nobody sneezed on the plates. We still had one more idea, and that is that possibly some photographic plates, especially like X-ray images, were sensitive to nuclear fallout from atomic bomb tests. And they could produce some kind of fog stars, maybe not exactly the same profiles. And we thought that this might have been an explanation, so we checked with the official atomic bomb test in the United States. Unfortunately, there were none that year. And since I'm not a conspiracy theorist, I went on further. So there's something that can actually produce these 9 objects that we see and later don't see. And that is if you would have either some emissions from something, let's say a non-human object in the sky, or reflections, solar reflections. And well, we know it's 1950, so there were no human objects there, but this is a possibility. And we wrote about it, and this started triggering my imagination because I, of course, want to know if there are more ways how one can test this possibility. This was the only thing we could come up with that actually worked for the paper. Of course, we couldn't write it that way. One has to always write it very, very conservatively if you want it published. So I started thinking about what are the other ways of predicting the signatures of these ET probes. Well, multiple transients is one of them. Then you can have triple transients if you have a rotating dish, I learned. But also you can have transients along a line. They don't have to be equally spaced. They can have different kind of spacing, and it depends all on the complexity of the geometry of these glinting objects. But once you have these very flat and reflective surfaces, you can simply have them along a line. So we sent this to ACT Astronautica. We had 2 or 3 referees. They were very happy with the hypothesis test. Perfect, accepted. And now I thought, let's just carry it out. So this is just, we learned, of course, also, I will just add as a parenthesis that if you have at least 4 of them, then it becomes a very good signature of that you have transients falling on a line associated with movement in the sky. And in that way, you can also even clearer say that these are no plate defects, as many people, or some people, I will say, are going to say is a risk that it is. So did we find something? Well, we actually did find some examples of these things. And I'm going to show you the top 2 candidates. We put them on archive last year. One is from the 6th of August, 1954. I list the probability. Also, and another, the best example is from the 28th of July, 1952. We will come back to this. And you see here also these 5 things that are there, and they just suddenly vanish. So it's kind of becomes very fun. Now, this paper I sent again to the journals. And once you write that there is some kind of, once you get a positive results, the journals get nervous. So it doesn't even go to review. It doesn't matter that we carried out exactly the same hypothesis test that we already had published, and we didn't deviate in any way from the published plan. This paper has a real issue even just getting to the review process. So what are the implications? Well, what I try to convey is that there is some very unexplainable flashes that come in multiples in the old photographic plates that shouldn't be there. And these are in plates taken before 1957. A possibility is that we see something artificial further out. A possibility is that there is, of course, still something wrong with the plates, but I think there's a lot of coincidences that have to line up for such plate defects to both appear in multiples and always perfectly imitating the stars, and at the same time being aligned in some cases. And of course, if it turns out, we actually estimated the surface number density of these objects. You can always go to the archive paper. Now there's something more fun. We have a new paper out. And this makes it even harder for the so-called plate defect hypothesis, because suddenly we have 3 very, very bright stars that you can see there that are beautiful, 2 overlaying and 1 here, that are seen there on the 19th of July 1952. And you look later, and we actually looked both half an hour earlier and 1 month later, and all this image we had, and they weren't there. Now, my colleagues were trying to see, can we explain this in some ways in terms of gravitational lensing? And they could possibly do it for this particular case if they placed something that was more or less a Milky Way supermassive black hole causing it, and not far from the Earth. And then you can do that. And then once you have 80 of these examples, you can start wondering a little. But let's say we didn't get closer to an explanation with this paper, but we really liked the very beautiful example that we found that gives even more weight to these multiple transients. You can see here is there in July 1952, it's not there in October 91. You can see it in Pan-STAR, you can't see it in Pan-STAR sighting, not in ZTF. And then we used the world's largest optical telescope at 10.4 meter on La Palma. Our colleague did beautiful images in the red, in the blue, and we saw nothing there. So we published a paper, discreetly written, and it got lots of, like hundreds of thousands of views on various YouTube influencers' channels. They got very interested. Now there's just something I want to share a coincidence with you. There's something very funny about the date that I didn't know about when we found the triple transients. Another of my friends, actually, my media agent, pointed out, you know, that date rings a bell. So then I went back and I decided to take a look at the other candidates, these aligned ones, at the top candidates that we had, because we had 5 candidates listed. And we have still a problem, that again, it coincides very close to these Washington events. And I'm going to say, it's just a coincidence, probably. So that is why we now are trying to figure out how can we test these multiple transients and actually find out if these were coincidences or if this is a real phenomenon, because I think it is a real phenomenon. We have like too many examples, but how can we test if this is related to, for example, reflections or emissions associated with non-human objects? This is the key question. And that we can do, and we have created a new project called ExoProbe that I'm leading. And I'm going to tell you about that because this is going to be completely new. We have just started it. And I'm going to argue again for why we should do it this way, because I believe in that extraterrestrial probes are highly likely. I think Avi has been giving many arguments for why this is such a realistic idea, because we humans can send something to another star. Why shouldn't they be able to send something to us? It's just natural. Think of Voyager, think of Pioneer. And you have 40 billion Earth-sized planets just in the Milky Way. And also, nobody said that they have to be biological in origin. You could even have some kind of AI and robotic little probes that are spread throughout the galaxy, and you can search for them. We couldn't do these searches in the 60s, because in the 60s they were talking about already like radio SETI versus searching for probes, but the technology wasn't there. The technology to do these searches came with the development of the CMOS sensors as you use in your mobile phone, when one digitized the old plate surveys or created new sky surveys like in the last 10 or 15 years. And that is when we developed the technology to actually search for ET probes. So now when we have it, why not do it? So I'm coming back to, again, the global network of telescopes that we want to work on. Of course, we're going to start with a minimum number. So the idea here is that just to repeat it for those who maybe forgot, is that we want to detect unidentified object. We want to validate it directly through multiple telescopes. We want to acquire the spectra and see what is it? Is it different? Is it similar? What are we actually seeing? And we want to localize it, because if you have many telescopes, there's something very beautiful about all that. You can localize it so accurately that you can go there and bring it down. And that's something that would be very neat to do, of course. So I work on this with several more scientists, primarily Geoff Marcy, who is our exoplanet pioneer and discovered the first, like 75% of all the first exoplanets. And also Brian Hill, John Gertz, and there are two more people who are involved, Alina Strebianska and Stefan Geyer. So we have a small team. This time we're going to go for a very small team to work effectively. And the goal is to find these short flashes, reflections or emissions, associated with artificial objects. And we're going to look for this very short, like 1 second long transients, because astronomers don't care about this parameter space. They have been looking for transients like supernovas that are there for months. They have been looking for things that are lasting for maybe hours, but this 1 second parameter space is almost entirely unsampled. So, of course, it makes it interesting even from astrophysics point of view. If you find some new phenomenon, or if you find some optical afterglow of a gamma ray burst, there are a lot of nice things that you can do here. I really like to explore new parameter spaces, like when we were looking for vanishing stars, because terra incognita is just so incredibly fun. And the goal is to detect, validate, localize, characterize, and finally, if you find something, bring it down to the Earth. I'm not ashamed to say it. So we started the project on the 1st of August, so it's a very new, and it's thanks to the support of a funder. And I'm going to walk you through the process of how it's going to work. So let's look here. First, we really need to select the appropriate instrumentation. And you cannot use just any telescope, of course, of any size, because you need very good tracking on the mount. You need very high optical quality when you search for these transients. And you also need a wide field of view. So some people say, oh, why don't you use just an amateur telescope? Well, of course, the amateur telescope has terrible optical quality, and also it's not going to fulfill any of your needs for the project. And you really need that tracking. And others are going to ask, so why don't you use some professional telescope like the JWST or Nordic Optical Telescope? And those of us who are astronomers know that it's incredibly difficult to get more than a few hours on any of these telescopes. And moreover, the field of view matters, because like JWST has a very small field of view. So if you're going to try to use any of those super telescopes, you're going to end up with something like much fewer of transients that you can discover. So you really need to balance it, have a balance between the field of view, the depth you search for, because you cannot use, let's say, mobile phones have a very big field of view, but they don't have very much of a depth. So all that has to work. We have selected that. Next, in order to verify and localize a probe, you need at least 2 telescopes, and the more telescopes you have, the more accurate you will have the location. And you can detect this flash in multiple synchronized telescopes, and that's what we want. And as they have a specific set distance that we have carefully selected, you will be able to measure the parallax and say how far the object is from us. Currently, we use currently we are planning 3 observatories, I would rather say, because I'm waiting for our main telescope that is much better than the other 2. We still need to think about how to upgrade these 2. The main telescope is going to be purchased the coming weeks. We have already put in an order, everything, and now it goes through the administrative process of Stockholm University. The third thing we do in order to make our life easier is that we skip everything inside the atmosphere. Off with the pigeons, off with the ducks and airplanes. We don't want to do anything of that, so we stayed outside the atmosphere. And not only that, we try to, in the initial phases, we are going to try to stay even outside the orbits where you have most of the human satellites. So we are actually probing the inner solar system. We also have a very efficient method to filter away all human satellites and space debris in one go as we observe. So this is something I'm very proud of. I hope I will be able to share this technique. I really like exploring new techniques to get rid of satellites. I can't help it. It's an obsession of mine since a time. We are going to use already existing techniques that also my colleague Geoff Marcy has been developing, where you can get real-time spectroscopy in a wide field, and that is so that we directly can characterize the thing. And of course, the goal is to add more telescopes, as I said. However, it's a little bit, there are some practical challenges with it, but that can allow us to increase the range of altitudes. And the more combination you have of these telescopes where you measure the parallax, the more better is your localization in 3D going to be. And of course, the most important, if the ET probe detection is successful, let's activate the space garbage collectors. I would hope to find some company that would like to help us to bring down the probe. And I wouldn't worry too much about if the probes agrees with me or not. So, and I think it will be a possibility to do so. I developed this program together with Dr. Marcy, as I mentioned, who discovered the first 70 out of 100 exoplanets and also received the Shaw Prize that he shared with the Nobel Prize winner Michel Mayor for his great discoveries. He's also the creator of the Breakthrough Listen program. And the Vasco team that have been working with me on these searches for transients and vanishing stars, as I mentioned, is it's a team of 40 people with diverse backgrounds, and we enjoy this work together. Here I had a very nice animation that I'm afraid I cannot show here. Somehow it doesn't work, but where you would be able to see how a flash here, how something is flashing, and as the globe is moving, different telescopes are seeing everything and are detecting this flash. And of course, those who are interested can come and I can show you the animation later. And with that, I very much would like to thank you again wholeheartedly for inviting me, and hope to talk more and discuss more.